So we'll talk about collision resolution for hash tables. The first idea is called separate chaining. So if you remember this slide that we saw previously, that we can end up having collisions, which means, two or more items can end up in the same bucket. Now, it doesn't really matter how good a hash function is, or the size of the number of buckets is prime or not. It's always possible to have collisions. So we must resolve that. So collision resolution is important part of any hash table. One approach to collision resolution is simply to allow each bucket to hold multiple items. And in order to hold multiple items, we can use another data structure. So this idea is called separate chaining, probably because each bucket is independent, and also the data structure in each bucket is typically a linked list, although it doesn't have to be. So before we see how separate chaining is implemented, you should know how it works. So try to work through this example using a very simple hash function that just the output of the hash function is the number itself, and see what kind of table you end up with. And assuming you've done that, this is the kind of table you should end up with, right? So for example, if you insert the number 14, the hash value is 14 and we modulo by 7. So 14 modulo by 7 is 0. So we put 14 into bucket 0. See 7 is also bucket 0. Now 16 modulo 7, that's 2. That's why 16 ends up in bucket number 2, so on and so forth. And also let's consider the load factor a little bit here. So if the load factor is, say, for 2, then that could mean the number of items is 200, number of buckets is 100, and on average there are about 2 items in each bucket. So, and when we each bucket is a linked list, then the lookup performance of a linked list of size 2, if it's always 2, then it's a constant, right? It's probably, it takes on average, sometimes it's 1 lookup we find it, sometimes it's 2 lookup we find it, so the average of 1.5, but that's kind of, a constant. Now, if we take it to the extreme though, if there is only 1 bucket, then again, we talked about this before, then all the items are stored in the same bucket. And in this case, the performance would kind of degenerate into that of a linked list, right? Which is O of n, and that's very, very not good. So the lesson from this kind of thought exercise is that we really should keep the load factor or the lambda very small. But how can we keep that? How can we do that? What if the number of items just keeps increasing, right? Well, we can, as the number of items increases, we can increase the number of buckets as well. So this is called table expansion or resizing. And we don't do this all the time. We don't do this in every insert. Obviously, that would be very expensive and unnecessary. We only do that when the load vector reach a certain value, right? Let's say when it reaches 2 or something like that. Then we're probably storing too many items per bucket. Then we can expand the table and we have to rehash all of the existing items into the new buckets. So why do we have to rehash everything? Well, look at this formula. What is the bucket index? The bucket index is the hash value modulo by the number of buckets. So in the new table, we change the number of buckets. So all the bucket indexes are different now. So that's why all the existing items in the new bucket, they might end up at different places, right? So that's why we have to just rehash and reinsert everything.